All right, so we're going to do an example, and the example is, I will switch over to the whiteboard view in a second, that if we have some charge QA, which is located at the origin, has a different charge QB at a different location, then we have to determine what the electric field is at a third point. I'm going to write down those values. QA is 8 coulombs at the origin, and QB is 3 coulombs at 2, 1, minus 1. What is E at 1, 4, 2, question mark. So now you should be able to see my video with my information about the problem. First thing I'm going to do, which is the first thing I always do, is draw a diagram. I'm going to zoom out a little bit. I am zoomed all the way out. I'll just move this over. Okay. Let me make sure I got that location right. Okay, yeah, 1, 4, 2. All right, so the first thing I'm going to do is draw a coordinate system because that is almost always the right thing to do. It's in 3D, so this is going to be my z-axis. This is going to be the x-axis, and this is going to be the y-axis. I always need to be in the situation where x cross y equals z. So y, although this is a 2D drawing, so you could, excuse me, I breathed something. You could view this in either direction. Y is pointing into the board here because I need for x, which lies in the plane of the board, crossed with y, which needs to be going into the board, to point in the z direction. Next, I've got to draw my charges. So my charges are QA, which is at the origin and has a value of 8 coulombs. And then I have QB, which is at x equals 2, y equals 1, z equals minus 1. So I'm going to go 2 steps in the x direction. I'm going to go 1 step in the y direction, and then I'm going to go 1 step in the z direction, and QB is right there. And then I have an observation point specified, which is that x equals 1, y equals 4, 1, 2, 3, 4, and z equals 2, 1, 2. This is my observation point. I'm going to name that P. How do we figure this out? Luckily, the charges, the electric field due to electric charges obeys superposition, which means that you can add up the field due to charge A and the field due to charge B. Where can I write that down? Superposition. If you have ever said or heard it said that something is superimposed on another thing, like there's one image on top of another image and you can see both of them, that is exactly the same concept, superposition. The thing is here, though, that I have two different things going on. So let's do the electric field due to A first. I'm going to move this diagram out of the way and scoot over here a little bit. And then I'm going to write down, I'm going to get rid of all this stuff again. That's at the origin, and that is at 2, 1, minus 1. Cool. And you got a nice view of my teacup. So the electric field due to charge A, which we will often write as just E sub A because it's the electric field due to charge A, is going to be charge A divided by 4 pi epsilon naught magnitude of our observation point minus the origin, which I'm writing as the letter O, squared, and then the unit vector in that direction. So that's, need a little more space here. I'm writing the vector observation point minus origin divided by magnitude of observation point minus origin, like that. That point is the origin, which is why I'm using the letter O to represent it. It's 0, 0, 0. So if I actually write all this out, observation point is 1, 4, 2. So this magnitude of 1, 4, 2 is magnitude P minus O. I'm sorry, I breathed some dust. Magnitude of P minus O is going to be 1 minus 0 squared plus 4 minus 0 squared plus 2 minus 0 squared, all square rooted. And then this thing ends up being cubed because we're doing it 3 times down here. So then what we end up with is 8 divided by 4 pi epsilon naught times, let's see, 1 plus 16 plus 4. So that's square root of 19 cubed. So we'll just write 19 to the 3/2. And then on the top, our unit vector becomes a hat x times 1 plus a hat y times 4 plus a hat z times 2. And all of that stuff gets multiplied by the 8. The 19 down here is to the 3/2 instead of just being the number 19 because we have it here on the top and the bottom. So that's the electric field due to charge A. And what we have to do is write down the vector electric field due to charge B and then add those two together. So, so you can actually see the bottom of the board there. Cool. EB is going to be QB, which was, yes?
Is this is the same example as, oh, never mind. I misread the section. I thought that was 21, not 19.
It's possible that I add, oh, it is 21.
Because we're doing EA.
Right. Yeah, it's 21.
Sorry.
I'm doing math in my head.
Am I reading that right?
No worries. Thank you. Okay. So, and then for charge B, what do we got? We are going to have P minus location B, which is going to be point B. So P minus B at the top. You can't see where I wrote that. But that distance, magnitude P minus B, or just a vector P minus B, is going to be equal to a hat x times 1 minus 2, so that is minus 1, plus a hat y times 4 minus 1, which is 3, plus a hat z times 2 minus 1, 2 minus minus 1, which is also 3. So the magnitude of this, magnitude of P minus B, is going to be 1 squared plus 9 plus 9, which works out to 19. That one's the 19 one. So then we end up with for electric field B, we end up with 3 coulombs times minus a hat x plus 3 a hat y plus 3 a hat z divided by 4 pi epsilon naught times 19 to the 3 halves. So these are my 2 electric fields. This right here and this, this right here. And I have to add them together, which means that what I have to do is add the individual vector components together, not the whole thing somehow. None of these numbers are nice, so that makes it kind of a pain. But the way that I'm going to do that is I'm going to simplify it and then just write down the individual vector components in this way, and that will be fine. So over here, I'm going to write that the total electric field, which we like to write as ET, is going to be 1 over 4 pi epsilon naught times. First, we'll do the x component, a hat x, times the contribution from EA, which is 8 times 1 divided by 21 to the 3 halves. So 8 over the 21 to the 3 halves, plus on the bottom here, we have 3 times minus 1 divided by 19 to the 3 halves. So let's turn this plus to a minus, minus 3 over 19 to the 3 halves. It's not a beautiful number, but that is what we get. Now we do the y component. So we write plus a hat y, and then we add the 2 y components together. On EA, we have 8 times 4, which is 32, if I'm not mistaken. So we've got 32 divided by 21 to the 3 halves. And on EB, we've got 3 times 3, which is 9. So we got to add those together, 9 over 19 to the 3 halves for the y component. And then the z component, which I just barely have room for down here at the bottom, is plus a hat z 2 times 8 right here is 16. So 16 divided by 21 to the 3 halves plus 3 times 3 is 9. 9 over 19 to the 3 halves. Wouldn't it have been nice if they just made both of these have distance 20? Well, square root of 20. That would have been wonderful, but that is not what they did. So my total electric field is this quantity, this whole thing right here. And then what I would do if I were solving this problem is I would enter it all in MATLAB or something and get numbers for these answers. And that would be that.